Good morning. So I am George Calas from Sorbonne University, the new name of the university in the center of Paris. And first of all, I want to transmit the best wishes of the French MINSOC and its members to their American mineralogist colleagues and cousins for this centenary celebration. Of course, we are all involved in the same wish to make mineralogy a success. So the first session of this celebration will concern sustainable development and the use of mineral resources, and the talks will be given by Gordon Brown from Stanford University and Mike Hochella from Virginia Tech and PNNL, Northwest Laboratories, concerning the impacts of the mining activity, and also on the future of our resources, so exactly in the topic of this first theme. And after their talks, I will encourage some questions about these talks, and we will, I am sure, enlarge the discussion to major topics related to the future of our societies.
Newly discovered environmental impacts of mineral resources utilization, direct and indirect incidental nanomaterials. So you're going like, what is an incidental nanoparticle, and what am I talking about by direct and indirect? And so let's just dive right in. This is great. Gordon mentioned the USGS and people like Murray and Larry who used to work there. They do a great job at mineral resources. And here you see their list of mineral commodities, their latest summary. They put this out every year, and it's like A to Z. Let's start with the A's. Abrasives, aluminum, antimony, arsenic, asbestos, okay? Yeah, asbestos is still mined and used, by the way. Let's go to Z or Y, yttrium, zeolites, zinc, zirconium, and all the other 85 things. There's one thing missing in here. This is an eye chart, but actually the thing missing here is the monster in the room, and it's coal. Coal is so important that it's actually in a different category. All this stuff comes from all over the planet. There's no place that doesn't have a mine, it seems. But look at the top there, more than 350 gigatons. A gigaton is 1 billion tons. So more than 350 billion tons of mined rock are brought to the surface each year on this planet. Think of that. One thing that's done is it's given us more than 30,000 acid-producing, Gordon just showed a couple of examples, acid-producing mine sites in the United States alone, and 100,000 acid-producing mine sites around the world. And every time I read this, and I read it 100 times, I think, how could that be? Another chart, I just want you to look at this part right here. Value added to gross domestic product and this is in the United States only, by major industries that consume processed mineral materials. That's 3,000 billion, that's $3 trillion. $3 trillion annually. This is for 2018. And the whole US economy is only, in quotes, 20 trillion. So that's 15% of our economy depends directly on the stuff that you guys study. That's a lot. Okay, now nano. I'm going to bring nano into this, of course. Nano is everywhere, and it's everywhere, and it's everywhere. Again, I've said it before, but if you're an oceanographer, if you're an atmospheric scientist, that's a dust storm. It's all nanominerals blowing across the Korean Peninsula there. If you're a volcanologist, if you work with rocks, metamorphic, igneous, sedimentary, whatever, you're going to find lots of nanomaterials. If you don't know that they're there, you should find them and see what they're doing and why they're important for you to study. From icebergs, how could they be in icebergs? There's a lot of nanominerals in icebergs, it turns out. Hydrothermal vents, rivers, whatever, continental margins, it's just all over the place. You can even see them from space. These are nanoparticles coming out of the Mississippi Delta. They impact the whole Earth. They're small things that are very powerful. For example, iron oxides that are weathered out of soils from continents go into the oceans either by rivers or by the atmosphere, actually more by the atmosphere than by rivers, believe it or not. The iron is a limiting nutrient of phytoplankton. Phytoplankton produce more oxygen for our atmosphere and consume more CO2 from our atmosphere than anything else on the planet, including all land plants. The population of these things are therefore very important, and their population depends on their source of iron. That's the most limiting nutrient they have in the ocean. Where does that iron come from? It comes from iron-containing nanoparticles. So these tiny nanoparticles that come off our continents affect the temperature of the planet by the CO2 consumption of these guys. And it adjusts the CO2 from the ocean to the atmosphere, and ultimately the temperature of our atmosphere. We recently published this in this paper. It's all new material. Humans make, that's 0.3 teragrams. This is in units of teragrams. So that's 0.3 million, so that's 300,000 tons of nanomaterials are produced every year that goes into products like, where's my iPhone? Your iPhone is loaded with nano circuits, nanoparticles as well, to make it work. And if you add all that together, it's about $1.5 trillion of economy every year comes from this 300 million tons of engineered nanoparticles that are made nanomaterials that are made every year. Incidental, like when a forest burns or when you have a factory, these are nanomaterials that are produced consequently, not on purpose, but there they are. They're called incidental nanomaterials, between 1 and 10 teragrams per year. Both of these are totally dwarfed by natural nanomaterials, like from dust storms or from volcanoes or from hydrothermal vents or sea spray or glaciers, or what the rivers bring to the oceans. Massive amounts, just from dust storms alone, on an annual basis, 320 million tons of nanomaterials go off into the atmosphere and travel the planet. Oh, by the way, you're breathing them right now. Okay. Also in this paper, we decided that we should talk about the nanomaterial cycle. There's a rock cycle, there's a water cycle, there should be a nanomaterial cycle. There is. It's never been conceived before, but here it is. You have earth components, everything you'd want here, human or naturally made. On one side of the triangle, you have nanomaterials on another part of the triangle, and you have the precursors to the nanomaterials. And you have various processes that you see here that bring you back and forth and around the loop or whatever way you want to go. Oh, by the way, this is an engineered nanomaterial. It's a carbon nanotube. Drivers of computers of the future, by the way. This is incidental. These are carbon nanoparticles from diesel exhaust. And here's a naturally occurring nanomaterial. We could have put a mineral there, but we didn't. We put a virus there. Viruses are great nanoparticles. They're about 40 to 50 nanometers in size. All right. So now we're going to get to these incidentals again. And, this is a mineralogy conference. Why should I be talking about incidental nanomaterials? Just wait till you see what I'm going to show you. So there are naturally occurring nanomaterials, of course, every mineral and every other naturally occurring material we know. Anthropogenic, made by people, and incidental. There are two kinds. Direct incidental is where they form directly from some human activity, directly from the human activity, like burning fuel in a diesel engine. You'll make fullerenes, which are carbon-containing nanomaterials. That's just one of zillions of examples. And indirect, and I'll give you an example of that in a minute. And then indirect incidentals are nanoparticles form as a result of anthropogenic earth modification. Oh, like mining. Gordon just showed you massive amounts of earth modification by mining. And when that happens, nature's going to go, oh, all these materials are in a different, now I'm in the oxic zone and I'm getting meteoric water on me, and now I'm going to make new nanomaterials that would not have been there unless it would have had the mining. Gordon showed that with mercury sulfide as one example of the many he showed. So these are called indirect incidentals. In terms of mining and everything else, Everything else you can possibly think of, we have direct and indirect incidentals, and they're really important, and a lot of them are mineralogic. George, how much more time do I have? 7 minutes, okay. So I'm going to start going faster here. This is the largest Superfund site in the United States. Whoops, sorry. Largest Superfund site in the United States. It's between Butte, Anaconda, and Missoula, Montana. It's 1,600 square kilometers of terribly contaminated land due to mining. You can see here, nanomaterials are involved. When you put mining and nano together, you get journal covers. It's really cool. This is a much smaller mining area. This is part of the 30,000 that are out there in the United States. This is a more typical size. This particular one I just picked, it's also in Montana, the Mike Horse Mine, it's called. And here's what it looks like today. I just flew over this last week just to take recent pictures for you. So here it is right here. It's only like 6 or 8 kilometers. But the reason I put it in here is because this is the headwaters right here of the Blackfoot River. The very famous Blackfoot River. If you've read The River Runs Through It by Norman Maclean, or if you saw the Hollywood movie The River Runs Through It, narrated by and directed by Robert Redford with Brad Pitt as a very young, wonderful actor in that movie, go see The River Runs Through It. It's a great movie about this stream. The Blackfoot River, one of the most famous fishing streams in the United States, was ruined from this mine. That's not good for the state of Montana economy. So you get the picture. All right, what does nano have to do with this? When you have dangerous elements moving down hydrologic gradients by hundreds and hundreds of kilometers, how does it get there? Because geochemically, it doesn't make any sense that metals should move that far. And the answer that we found over the last 20 years is that the metals are moving in nanomaterials. And you can see them by scooping up muck out of streams and doing a lot of sophisticated looking. Look at these scale bars. These are tiny, tiny things, and they're moving all the heavy metals downstream. And so all the bioavailability, all of the transport of these things has to do with nanomaterials. You can go to Spain. This is the Iberian Peninsula. Here what the streams look like from acid mine drainage. And again, you're seeing these nanomaterials. And let's see if I can play this movie. This is Schwartmanite. Gordon showed how, I'll let that stop for a minute, how arsenic goes on the surface of iron oxides. What was it, magnetite? Yeah. And this is how arsenic goes on the surface of Schwartmanite, which is a iron oxyhydroxide sulfate nanomineral. And see the little nanofibers coming out of this? I mean, nano, look at that, 10 nanometers, they're really small. And when you do electron tomography, which is our latest, greatest thing, I think we do the best in the world at this, this is what these minerals look like. Look at those tiny nano-sized fibers, and they're just loaded with arsenic. And it's created a problem since Roman times, and it's still not fixed on the Iberian Peninsula. Now we go to my last example, which is we published here, and it's the discovery and ramifications of incidental. So what I just showed you, those are all indirect incidentals. This is a direct incidental. These nanomaterials are going to be made directly by what humans do to rocks, basically. And they're going to do that by burning coal. And so here's coal. My wife and I were just in the Powder River Basin of Wyoming, which is just across the Montana border. And I've never seen, look at this coal, these coal seams are ungodly big. 3.7 gigatons per year of coal is mined worldwide now. And you know, we burn it here, and we do a lot of interesting things to our atmosphere. Everybody knows about that. 18% of the coal doesn't burn under the conditions of coal-burning power plants, so you make ash, and you have a lot of ash then from gigatons of coal that we burn every year. And the point here, is my last slide, there are trace minerals in coal. And one of the most common ones is titanium oxides. It's either rutile or anatase. And it's between 1% and 3% of all coal. So when you burn coal, what happens to the TiO2? And that's what this paper was about. A lot of it ends up in the ash. And when ash dams break, you get national headlines that NPR and everybody else talks about because the ash goes into the river. And there's the ash that's ash dam broke, it goes into the river, and here it is. Now everything dies in the river because of the arsenic contamination. The arsenic contamination, as Gordon would not be surprised, is from ferrihydride in this case that we found in the river. No one knew that before. But when you look at TEMs at this ash that's in the river, you find these very strange titanium oxide minerals that aren't anatase and rutile anymore. There's something else. It turns out they're McNeely phases. And these tiger stripes are your key that you're looking at a McNeely phase. So this is only to show you that we went around the world and collected ashes from around China and all over the United States, and we found these McNeely phases everywhere, and all these ashes had McNeely phases. And so here's what they look like in more detail. Here's the formula for a McNeely phase. They're oxygen-deficient TiO2s. And McNeely phases are these formulas. See how they're oxygen-deficient? That should be Ti408, but it's Ti407. So one oxygen out of every 8 is missing. And you get these different stoichiometries. And you can tell them apart. Michael Schindler, who's going to speak next, helped us do this. It's really difficult, but you have to find C star. When you find C star, you can measure these repeats, and then you can tell exactly which one you have. And then we can synthesize these things in the laboratory and make them, because now we figure, oh my gosh, these things are all around the planet. When you burn coal, you're going to get these McNeely phases. So I'm thinking, wait a minute, these are oxygen-deficient TiO2s. They have really strange properties, especially when they're nano. And we looked into that, and we were right, and then we thought, does that mean we're breathing this stuff? Is this important? Well, yeah, it's important. It's really important. So important that, and I'm almost done, George. This is a paper that we now have in review in Environmental Health Perspectives, which is the most important journal in the world to put stuff like this. And I'll just read the title, and that's all I have to read here. Oh, by the way, this is a mouse lung that we've given these synthetic McNeely phases that are just like what comes out of a coal-burning power plant. Pulmonary exposure to McNeely phases, McNeely phase titanium suboxides results in significant macrophage abnormalities and decreased lung function. Oh my gosh, this is not good. How much of this stuff have we made since the Industrial Revolution? About a gigaton. Where is it? It's everywhere. I could go outside this building and find it. All I do is sweep up dust off the street, and we'll find it for you. So when we published this first Nature Com paper, it got international press. This one is just going to blow the socks off of, because this is what we breathe, and it's not good. I'm going to skip this last slide. We can talk during the discussion of what all this means in terms of mining sustainability, because there's a message in that, but we'll leave that for the discussion. And I just want to end with one more time, nanoart.org. If you don't contact me, I'll contact you. Thank you very much.